When you stand next to a massive piece of industrial machinery, like, say, a towering oil storage tank or one of those heavy-duty gearboxes at a cement plant, you naturally assume it's this impenetrable fortress.
Oh, absolutely. I mean, you're looking at inches of solid forged steel.
Right. And the instinct is to think that, well, absolutely nothing is getting in or out of that system unless an engineer deliberately allows it.
Yeah, it creates this really powerful illusion of isolation. You just see this closed loop of sheer mechanical force that looks totally walled off from the world.
But if you look closely, usually right at the very top of these metal giants, there's a mechanism that just shatters that illusion entirely. Because these massive multi-ton machines are actually doing something that seems, I don't know, surprisingly biological. They're breathing.
They are. And, that biological comparison is actually incredibly apt. Because just like our lungs, machinery is constantly inhaling whatever happens to be in the immediate atmosphere.
In an industrial setting, that atmosphere is, well, it's pretty brutal, right?
Oh, it's rarely clean. It's usually this highly destructive, completely invisible cocktail of microscopic dust, airborne particulates, and ambient moisture.
Which brings us to our topic. Welcome to today's deep dive. We are exploring the hidden high-stakes world of industrial contamination control for you today. Specifically, we're looking at the engineering behind Sentry products, their desiccant breathers and adapters.
Yeah, it's a fascinating area.
It really is. And our mission for you today is to unpack the physics of exactly how and why these mechanical behemoths actually breathe, and how controlling that breath at a microscopic level is, well, often the only defense against catastrophic equipment failures.
Which is a highly critical mission, because honestly, contamination is the silent killer of heavy industry.
Right, because we just see the big parts.
Exactly. We naturally focus on the visible components, right? The gears, the torque, the immense pressure. But the reality is that even a microscopic amount of water getting inside a hydraulic reservoir fundamentally degrades the fluid.
Like it ruins the oil itself.
Yeah. It compromises the oil's viscosity, it accelerates oxidation, creates rust on the internal surfaces. I mean, it ultimately just tears the mechanical system apart from the inside out.
Wow. Okay, so to really understand how engineers defend against this invisible threat, we have to look at how the standard of protection evolved. And from the source material, the turning point seems to be 1997.
Yep. 1997 was huge.
That was when Sentry essentially re-architected how machinery interacts with ambient air, right? They set what became the industry standard.
They really did, because prior to that point, breather technology was effectively just a screen, or maybe a really rudimentary filter.
Just to keep the big chunks out.
Pretty much. I mean, it kept the rocks out, but it didn't do much else. But in 1997, Sentry introduced a fully integrated system that combined replacement desiccant cartridges with check valve technology.
And that changed everything.
Totally. By doing that, they moved the whole industry from just passive ventilation to active contamination control. It drastically reduced moisture and particulate intake and, lowered maintenance costs at the same time.
So I want to break down exactly how that works for our listeners, starting with the desiccant itself. They designed these breathers with a 360-degree clear view casing, which honestly seems purely practical, right?
Oh, it's very practical.
Yeah, an operator can just walk the factory floor and visually verify if the thing is actually working. They're looking at this inert silica gel inside the casing that starts out as this bright gold color.
Right.
And then, as it pulls moisture out of the air, as it absorbs the water, it gradually transitions to a dark green. It's kind of like those little do-not-eat packets you find in beef jerky, but blown up to industrial scale.
That's exactly what it is. And that visual feedback loop is vital for maintenance. You're never, guessing whether the internal components are protected.
Because you can just look at it.
Exactly. The chemical reaction inside the silica gives you absolute real-time proof that moisture adsorption is actually happening.
Okay, I do need to ask you about that word, though. Adsorption. With a D.
Oh, yeah.
Because I think most of us assume these things work like sponges, just absorbing water. What is the actual physical mechanism happening with that gold gel?
Yeah, so it's an important distinction to make. Absorption with a B is when a fluid permeates or dissolves into something completely, like your sponge analogy, it completely integrates.
All right, soaking up a spill.
Exactly. But absorption with a D is strictly a surface phenomenon. So silica gel is engineered to be incredibly porous at a microscopic level. It has this massive internal surface area.
Okay.
So when humid air passes through it, the water molecules actually physically adhere to the the vast surface area of those tiny pores.
Wow.
It traps the moisture without the silica itself dissolving or, changing its fundamental physical state.
Ah, okay, that makes sense. But it does bring up a major operational question for me. If this silica gel is just exceptionally good at grabbing moisture and it's sitting on top of a machine in, say, a superhumid paper mill,
I see where you're going.
doesn't it just saturate itself immediately? I mean,
Yeah.
if the factory air is damp, won't this highly efficient gel just pull in moisture continuously, even if the machine is turned off? Like, wouldn't you just waste the cartridge in a day?
That is precisely the vulnerability that their 1997 check valve integration solved. Because you're right, a breather without check valves is just an open airway.
Right, it's just sitting there breathing humid air for no reason.
Exactly. It's constantly exposed. But by integrating check valves, the breather actively manages the airflow. The system actually remains entirely closed off from the outside atmosphere until the specific moment the machinery requires an exchange of air.
Oh, so it only inhales or exhales when mechanically necessary. It's basically holding its breath the rest of the time?
You nailed it. The desiccant is completely shielded from ambient humidity. It only goes to work when the machine's operation creates a physical demand for airflow.
Which obviously makes the gel last a lot longer.
Dramatically longer. By restricting exposure solely to those active breathing cycles, the lifespan of the cartridge is vastly extended.
Okay, that perfectly explains the baseline mechanics, but I want to look at how this scales up. Because, pulling a little bit of moisture out of a small gearbox is one thing.
Yeah.
But industrial environments are wildly diverse.
Very much so.
Let's look at their D-series, for instance. This is engineered for large stationary applications, huge oil storage tanks, massive fluid reservoirs, power grid transformers. And the specs here really highlight the sheer scale of the problem.
Yeah, the D-series is a beast.
Right. It uses 100% silica gel for maximum moisture capacity, but it also integrates a 2-micron solid particle filter. And it has to manage an airflow of up to 20 cubic feet per minute.
Which is huge. When you combine those three factors, the 100% desiccant, 2-micron filtration, and 20 cm airflow, you start to realize the immense mechanical stress these systems are under.
20 cubic feet per minute sounds like a windstorm.
It's a massive volume of air rushing into a machine, and filtering that at 2 microns is incredibly fine. I mean, in heavy machinery, the tolerance between interlocking gears or inside hydraulic pumps is minuscule.
So even tiny dust matters.
Absolutely. If even a 5-micron or 10-micron solid particle bypasses the filter, it becomes an abrasive wedge. It'll score the metal, generate secondary wear debris, and just kick off this chain reaction of mechanical degradation.
And that's just for stationary equipment in, relatively standard conditions. What happens when the environment itself is overtly hostile? I'm thinking of paper mills with constant high humidity, or mining quarries with relentless dust, or even facilities with high-pressure steam cleaning.
Well, that requires an entirely different engineering architecture. You have to move from the baseline disposable models to highly durable managed pressure systems, like their X series.
Okay, so how does the X series handle it?
In extreme high dust or high humidity environments, you really can't rely on a simple open and close valve. So the X series utilizes a reusable top cap that houses 2 distinct check valves, one specifically for intake and one for exhaust.
And the mechanics of those dual valves are fascinating. The intake valve is calibrated, so it only opens when the pressure differential, the difference between the outside atmosphere and the internal tank pressure, hits a very specific threshold of 0.1 psi.
Yes.
They refer to this as the cracking pressure. And the exhaust valve operates on the exact same threshold, just in reverse.
Exactly. And that 0.1 psi threshold acts as this rigid mathematical gatekeeper. It guarantees that the hydraulic system is hermetically sealed against that humid paper mill or the abrasive quarry dust.
He just locks it out.
Completely. The internal environment is isolated until the internal pressure shift becomes significant enough to actually force that valve open.
I have to challenge this whole concept, though. I mean, looking at this, if we are engineering dual check valves with 0.1 psi tolerances just to keep the outside air away from the oil, why are we letting them breathe at all? If moisture and dust are so destructive, just weld the tank completely shut. Make it a submarine. Seal the environment entirely, and you never have to worry about a 2-micron particle getting in.
It is a very logical assumption. But unfortunately, applying submarine logic to fluid dynamics and thermodynamics inside an industrial machine leads to catastrophic failure.
Wait, really? Why?
You have to consider what is actually happening inside that tank. You have industrial pumps constantly moving massive volumes of fluid in and out of the reservoir. When a pump draws hundreds of gallons of oil out of a sealed tank, it creates a void.
Okay, and nature abhors a void.
Right. If the tank is completely sealed, that displaced volume instantly creates an immense internal vacuum.
Oh, like trying to suck a highly viscous fluid through a perfectly sealed container. Like a thick milkshake through a straw.
Precisely. And what happens is cavitation. The pump is demanding fluid, but the vacuum is resisting. The resulting pressure drop causes the fluid itself to essentially boil at room temperature.
Boil without heat.
Yeah, it forms these microscopic vapor cavities, bubbles, basically. And when those bubbles pass into the higher pressure areas of the pump, they violently collapse. These microscopic implosions actually pit and tear away at the solid steel of the pump internals.
Wow. So a sealed tank physically destroys the pump.
Yes, it does. And the reverse is also true. If you pump fluid back into a completely sealed tank, you severely compress the remaining air, creating dangerous outward pressure.
That makes sense.
But even if the fluid levels remain perfectly static, you still have to contend with thermal expansion. Industrial machines generate intense heat. As the air and the oil inside the tank heat up, they expand.
And if it's welded shut, it's basically a bomb.
Exactly. The escalating internal pressure has nowhere to go. It will eventually warp the metal walls, blow out the industrial seals, or just violently rupture the tank itself.
Oh, I see. So the machine physically has to equalize its internal pressure with the outside world. It literally doesn't have a choice.
It has to breathe to survive. That is exactly why the 0.1 psi cracking pressure is such an elegant compromise. It maintains a tight seal against the toxic ambient environment for the vast majority of the time, and only briefly opens the lungs to equalize pressure before structural damage can occur.
Okay, that is brilliant. And I notice for environments where the physical environment involves actual streams of water, like food processing facilities or cement plants that do frequent high-pressure washdowns, they engineer physical deflectors too.
Yeah, the X100.
Right. The X series utilizes an add-on called the X100 washdown cap. It acts essentially as an armored umbrella. It ensures that the kinetic force of a pressure washer doesn't accidentally trigger those 0.1 psi check valves and just inject water straight into the machinery.
Which perfectly transitions us to the next tier of engineering challenges. Because everything we've discussed so far is about defending against the outside environment. But what happens when the threat originates from within the tank itself? Oh, right.
Or, when the physical impacts are far more severe than just water spray.
This is where we look at their premium architecture, right? The Guardian series. When you look at the physical construction of the Guardian, they abandon standard industrial plastics entirely. The casing is constructed from a patented material called Triton.
And that shift to Triton is a masterclass in material science. Standard polycarbonates and industrial plastics are super susceptible to chemical embrittlement and microfracturing.
They just wear out.
Right. Over time, constant exposure to thermal cycling getting incredibly hot, then cooling down combined with chemical exposure causes standard plastics to become brittle. And in a heavy industrial environment where tools are dropped or machinery vibrates violently, a brittle casing becomes a critical point of failure.
So Triton fixes that.
Yeah, Triton is highly resistant to both harsh chemicals and high-impact kinetic force. It maintains its structural integrity across severe temperature fluctuations.
So the armor's better. But the internal engineering of the Guardian solves a problem I honestly hadn't even considered until reading this. You mentioned the threat coming from inside. Some industrial fluids, particularly in specialized applications, produce incredibly volatile corrosive fumes.
They do. And if those corrosive vapors are constantly being exhaled up through a standard breather, the chemistry of those fumes will actually attack the silica gel from the bottom up.
Oh, wow.
Yeah. The desiccant is highly effective at capturing external moisture, but it can be rapidly degraded by volatile organic compounds exhaling from the oil. It basically destroys the defense system from within.
And to counter that, the Guardian series integrates an isolation check valve. Its entire purpose is to isolate the adsorbent silica gel from the exhaust air, right?
Exactly.
It physically routes volatile fumes and internal fluid splashes away from the desiccant. And because of this specific chemical isolation, the Guardian is actually the only breather series that Sentry recommends for diesel fuel applications.
That is a vital specification for you to understand, honestly. Diesel fuel off-gases continually. Without an isolation check valve, the constant exhalation of diesel fumes would rapidly saturate and destroy the silica gel.
It'd be useless in days.
Yep. It's a highly targeted solution. Though we should note, it is strictly recommended for diesel, not for other types of highly volatile fuel applications.
Good to know. Now, beyond the chemical resistance, the physical architecture of the Guardian series is entirely modular. You aren't just buying a static filter. You're building a layered defense architecture tailored to the exact vulnerabilities of a specific factory.
And modularity is a profound advantage in industrial engineering. Facilities don't want to stock a dozen different proprietary breathing systems for a dozen different environmental variables. A modular framework allows an operator to utilize a base Guardian unit and scale its defensive capabilities on demand.
It's like Legos. You can physically stack components. They engineered a modular stackable ring, which allows an operator to attach additional desiccant cartridges linearly, extending the service life in high humidity areas.
Yep, stack them up.
You can use that same ring to introduce an activated carbon filter module to scrub specific exhaust vapors. You can even integrate a compound indicating gauge directly into the stack to get highly accurate, real-time telemetry on the internal pressure and the filter's operational lifespan.
And the most significant modular addition is the high-capacity air filter. This can be run in tandem with the desiccant or just as an independent particle defense. What makes it exceptional is the inclusion of a 0.3 micron HEPA filter.
Wait,
It operates at 99.97% efficiency.
I have to pause there. A 0.3 micron HEPA filter attached to a massive grinding industrial gearbox. I'm trying to picture how a filter that fine even functions in a setting that dirty without instantly clogging.
It is an extreme level of precision, I'll give you that. We established earlier that 2-micron filtration is critical for preventing gear abrasion. Dropping down to 0.3 microns at 99.97% efficiency. That moves the defense from heavy mechanical protection to a clinical, almost sterile standard.
Like an operating room.
Basically. At 0.3 microns, you are filtering out particles that operate under Brownian motion particles so small they don't even follow standard aerodynamic flows. Attaching that level of filtration to a heavy-duty hydraulic reservoir is just an extraordinary commitment to contamination control.
It is an incredible technological achievement. But when you look at this entirely sealed, Triton-encased, dual-check valved, 99.97% efficient artificial lung, there is a glaring, almost absurd, fatal flaw in the entire philosophy.
The human element. Maintenance.
Exactly. You spend thousands of dollars engineering this hermetically sealed, perfectly isolated environment to keep the internal oil pristine, and then routine maintenance is required.
And it all goes out the window.
Right. A mechanic walks up to the machine, physically unscrews the main cap to top off the hydraulic fluid or pull an oil sample, and instantly the tank is wide open. The seal system is broken, and all that dusty, humid factory air floods right in.
It really highlights the ultimate irony of mechanical engineering. The very act of maintaining the equipment becomes the primary vector for contamination.
It's crazy.
You can maintain a clinically sterile environment for 6 months, only to introduce a massive, catastrophic dose of ambient humidity and particulate matter in the 10 minutes it takes to conduct a routine oil change. This is exactly why advanced breathers are ultimately ineffective without the final piece of the architecture, the adapters.
The adapters exist entirely to solve the human problem. They ensure the loop is never broken.
Precisely. Let's look at their gearbox adapter kit as a prime example of closed-loop engineering. It allows the desiccant breather to be permanently installed onto the gearbox.
Sure.
But critically, the adapter integrates quick connect ports. This architecture allows a maintenance team to hook up hoses to pump new oil in, extract degraded oil out, run external offline filtration, or even safely draw analytical fluid samples, all while the primary system remains completely sealed off from the atmosphere.
So the tank is literally never exposed. The mechanic never pops the lid.
Never. The adapters transform contamination control from a standalone filter into a comprehensive closed-loop operational philosophy. It completely eliminates human-introduced exposure during routine procedures.
And the engineering of these adapters has to account for the same environmental extremes as the breathers themselves, don't they?
Oh, sure.
For example, their splash adapter is a fascinating piece of fluid dynamics. It's designed specifically for mobile equipment, heavy construction gear, massive mining haul trucks. When a multi-ton vehicle hits rough terrain, you have hundreds of gallons of hydraulic fluid violently sloshing upward inside the reservoir.
Yeah, that kinetic energy is immense. If that fluid impacts the bottom of the breather directly, it can coat the filters and destroy the desiccant cartridge instantly.
So the splash adapter utilizes internal baffling. The geometry inside the adapter physically channels the kinetic energy of that violent upward slosh, deflecting the fluid safely back down into the reservoir. It completely shields the fragile HEPA filters and silica gel above it.
It's really smart. They also engineered domed flange adapters, which provide a rugged, low-profile physical mount for static hydraulic reservoirs, along with multi-thread adapters to integrate with various global pipe thread standards like NPT or BSPP.
There's an adapter for everything.
Pretty much. But from an operational safety standpoint, one of the most critical features is their use of colorized quick connects.
The colorization is a brilliant piece of idiot-proofing. The quick connects are anodized in specific colors that align with the established oil-safe color spectrum.
Yeah, it creates an immediate visual confirmation system. A maintenance technician simply matches the blue quick connect on their fresh oil transfer cart to the blue quick connect on the gearbox adapter.
So you can't mess it up.
Right. It removes the guesswork and drastically reduces the risk of accidentally introducing an incompatible fluid into a highly specialized mechanical system. And the engineering even accounts for slight variations in the anodized shading, ensuring the physical performance of the connection is never compromised while maintaining that critical visual safety cue.
Wow. Let's pull back and look at the trajectory of what we've unpacked today for our listeners. We started with the assumption that heavy industrial machinery is a sealed, impenetrable system. We realized that thermal expansion and fluid displacement mean these massive machines constantly have to breathe.
Yep, the submarine logic doesn't work.
Exactly. We explored how Air Sentry shifted the paradigm by integrating active check valves and visually verifiable silica gel, turning a passive hole into a controlled airway. We saw how the engineering escalated to manage 20 cubic feet of air per minute, how dual valves with precise 0.1 psi cracking pressures isolate extreme environments, and how advanced Triton materials and isolation valves defend against chemical degradation.
And ultimately, we examine how modular HEPA filtration brings clinical-level defense to heavy industry, while specialized adapters and quick-connect architectures completely remove the human vulnerability, sealing the closed loop permanently.
So as we wrap up this deep dive, why does understanding the microscopic physics of industrial breathers actually matter to you?
Well, it matters because our entire modern existence relies on the continuous output of manufacturing and global supply chains. When a critical gearbox in a paper mill, a cement plant, or a power grid fails due to internal rust or microscopic abrasion, the consequences radiate outward.
It's not just a broken machine.
No, it halts production, it disrupts supply chains, and incurs massive repair costs. Defending these industrial behemoths against microscopic contamination with highly engineered intelligent systems keeps our critical infrastructure running smoothly and efficiently.
It is the invisible, highly calibrated shield that keeps the heavy machinery of the modern world turning. And it leaves me with this final thought for you to ponder. If brilliant engineers are going through the immense physical and chemical trouble of designing modular, Triton-encased, 99.97% efficient HEPA-filtered artificial lungs just to protect the internal oil of a steel gearbox, take a look at the environment around you right now. What other inanimate systems in your daily life are secretly inhaling, expanding, and breathing, and what exact microscopic cocktail are they pulling from the air?